Okay, so let's talk 2.4, number 8. So, looking at this thing, your first step should be probably to figure out what kind of beast this thing is. So, what do you see here in terms of classification?
Non-linear Bernoulli initial value problem.
Okay, yeah, seems like a Bernoulli. I look at this side here, I see something that looks like a first order linear ODE, and then there's this weirdness on this side, which is y to a power times some function of x. Okay, yeah, I believe this is Bernoulli. So what's my technique for Bernoulli?
Well, okay. I'd like to see how you do it, but my first step is solve the left side as a linear homogeneous equation.
Yep, perfect.
I have a quick question too. Could you basically just treat this as a normal uh, variation of parameters problem pretty much? Except
Yeah, so that's kind of the trick with Bernoulli equations. There are two techniques here. Technique one is that you can treat it as first order, linear, non homogeneous, and just do variation of parameters. That's kind of the first order thought. That's the one the book does. That's the one I tend to prefer. There is another technique you can use here. So if you see these on the internet, they'll do this thing where they guess something of the form like, oh, I'm gonna have to remember exactly what it is. There's a there's a very specific guess you can make, and I believe that guess amounts to. I've completely forgotten now.
Because I
That's
keep
disappointing.
seeing this online. You're right, and it's like there's a function like v that you substitute in.
Yeah, it's like y is t to the r or something. Oh no, it's v. This is not right. That one's for a different one. It's crap. Okay,
It involves y1 or something like that.
yeah, yeah. I don't want to waste a bunch of time, but there is another substitution which I have now forgotten and should look up. But there is a substitution you could do. I really prefer this first thing so much that I've apparently completely forgotten this other substitution.
If
If you
you were
look back through
looking it
my,
up, do you know what you would look up?
yeah, it's the Bernoulli substitution.
Ty, can you mute your mic, please?
All right. At any rate, I'm going to solve this kind of linear part as though it was homogeneous. So
I have it pulled up. V is equal to y raised to the power of 1 minus n. And then it says y is equal to 1 minus, parentheses, minus 1 is equal to y squared.
hang on a second.
Okay. So then, yeah, this is y, or which is equal to, so y raised to the power of 1 minus n is equal to y raised to the power of 1 minus, parentheses, minus 1.
Oh, you're looking at an example.
Oh.
Yeah, I see it's v prime equals 1 minus n times
Yeah,
y
so in this
minus-
case, the n that they're talking about is 3/2. So in my case, I'd guess 1 minus 3/2 here.
Got it. Yeah, this is the solution that every DE calculator I've seen online seems to use.
Yeah, this is a really standard method. The one thing that I really like, one of the reasons that I actually really like this book is he leans a lot harder into the idea of there's one technique that'll do a lot of these at once, and that technique is variation of parameters. Like if you took this course from me, say 6 or 7 years ago, I would have taught this whole course with a like there would have been many more techniques involved. But the thing is, if you just lean a little bit into variation of parameters, you can not memorize so many different techniques. You can just use variation of parameters robustly. Um, So I used to touch variation of parameters as like a like a one-day topic. Like, oh yeah, there's this other technique called variation of parameters, but instead let's just memorize all this other shit. And now I've flipped that completely around, and I think that's an improvement.
So I know we shouldn't stick on this for too long, but would there be a situation in which the second method would be better or work when the second one or the first method wouldn't?
No, Bernoulli equations fall to both of these techniques,
Okay.
which is why I tend to lean into the variation of parameters one, because it always works and I can use it for other stuff.
Yeah, I was gonna say if the first method doesn't work, but the second does for some instances, I was like, well, yeah, teach us the other one, but yeah, that doesn't matter now.
Yeah, if there were any advantage at all to the second technique, I would be teaching that one, but there isn't.
Okay.
I am actually a real fan of variation of parameters as a solution method. It makes a lot of sense in my head. The way,
yeah,
at least
a really
the way I noted
cool
it.
technique, and we'll see that it works in several cases where there's no reasonable expectation that it should work. It just kind of does. It's sort of a miracle of applied math, actually. All right, how do you solve homogeneous linear equations? What do you do?
Separation of variables.
Okay, so we're going to get y prime is x times y. So we're going to have dy over y is x dx. Integrate both pieces. So we're going to get the natural log of the absolute value of y is x squared over 2 plus a constant. You guys all on board with this? Am I going too fast with this?
You're good.
Okay, so we're going to get y is a e to the x squared over 2.
Great.
And that really should, I guess, be denoted as the like homogeneous y.
Right, not the actual y, but
Or y1 in the textbook.
yeah, they use it as y1.
The textbook writes y1. I tend to write yh. Whatevs. The textbook is leaning into the idea that later there will be a couple different homogeneous solutions. I'm kind of leaning into the idea of there's a homogeneous solution. Let's go find it. But all right, so we found the homogeneous thing. Now what do I do with that?
Substitute
Take the
a as
derivative.
for a function u, and then take the derivative.
Yep. So now we're on variation of parameters, and variation of parameters here looks like I'm going to guess y is some function mu e to the x squared over 2, and that kind of important bit here is that mu here is a function of x. Okay, so now I need to do some stuff to this. So my first thing I'm going to do is I'm going to differentiate. And now this is the thing that you can pretty easily screw up here, because here I need a product rule. You guys with me on that?
1d2 plus 2d1.
Sure. Yeah. So mu prime e to the x squared over 2 plus mu e to the x squared over 2 times x. Okay, now what do I do with these?
Substitute them back into the original equation along with the value for yh.
Okay.
Do you need your plus c's? I forget in this case.
My plus c's.
There aren't any because
Oh
you're
no, you differentiated.
yeah,
Never
you
mind.
differentiated.
Yeah,
Okay. So now I'm going to take these and I'm going to put them back into my original differential equation here, which I'm going to call star. Right, so now star gets evaluated, and it's going to become, and I guess I can save myself just one kind of step here. So it's y prime minus x times y. And this is supposed to equal x times, now I've got this whole function y here. So I've got mu to the 3/2 power times e to the x squared over 2 all to the 3/2 power.
I have a feeling this is the step where I was going wrong because I've got the exact same thing you do all the way up to this point.
Okay. Yeah, so this is ultimately the step where I would expect things to go wrong with you guys. Because honestly, you guys are pretty good at solving homogeneous equations, I think. It's not separating variables is something you've been practicing for a while, so I think you're probably getting good at it. The variation of parameters guess, as long as you're remembering the product rule here, is pretty straightforward. It's this step where there's going to be a bunch of algebra that's really going to be the problem. So the first thing that I should see here, and this is always going to happen, when I make this substitution, I should always expect cancellation. If there's not cancellation going on here, I have solved my homogeneous version wrong, and I need to go back to it. Does that make sense?
Yes.
Okay, so the cancellation that I'm expecting to see is right here. That's those two things add up to nothing. And
Now,
then
Can you also, oh, sorry, go ahead.
no, go for it.
Can't you also cancel that e to the x squared over 2? Can you divide both sides by that to reduce the outer exponent on the right side to 1 over 2?
Yes. So I'm gonna just rewrite this whole thing, right? So in order to not lose myself, I've got mu prime e to the x squared over 2 is going to be x mu to the 3/2 times, and then this thing represents, right? This thing raised to the 3/2 power. So that's one of those, an e to the x squared over 2 times a half of one of those. You guys all with me on my kind of exponent management? That's really I'm kind of thinking a to the 3/2 is a times a to the 1/2. Okay, and now I'm going to see some more cancellation here. I'm going to see that, oops, that's not going to work. I'm going to see that this term here cancels against that term there by dividing. And then ultimately here, I'm going to move the mu things to the left. So I'm going to have mu to the, oops, and rightfully so, you guys should be complaining about my handwriting. I'm going to have mu to the minus 3/2 d mu is, and then on this side, I've got an x, an e to the something, and then a dx. What's the power on that e here?
It's x squared over 4, right?
Good. Okay, now integrating both sides, what do I get?
Negative 2 mu to the negative 1/2, right?
Okay, let's see. So this guy is going to be, integrating. I'm going to have a mu to the minus 1/2, right? To the 1 higher power, and then over the 1 higher power, which you're right, simplifies to minus 2 times mu to the minus 1/2. And then that's going to, on the other side, I'm going to need to do a little something something over there. What are you going to do over there?
U sub.
Yep, well, yeah, exactly. U sub.
Yeah, I do a little u sub, so I got x squared over 4 is my u, so my du is going to be, well, I guess x over 2, right? Dx. Okay, so I got that piece. I need an over 2 here, so I need a 2 on the outside. And so here I'm going to get 2e to the x squared over 4 plus a constant. Then I should probably check that I integrated right. So if I differentiate this, I'm going to get e to this stuff, and then the derivative of this thing's going to be an x over 2. Okay, cool. Feels like I got it. All right, now what?
Solve for mu.
Yep, now I'm going to solve for mu, so I'm going to multiply through by, well, I'm going to multiply through by minus a half, I guess. So I'm going to get mu to the minus 1/2 is, well, I think I got minus e to the x squared over 4 plus some constant. You guys with me on that? Okay, next up. How do you get this out of there?
What I do is
Square it.
I
Oh.
send it to the bottom first, and
Yeah.
then I flip both sides and then square it.
Okay, I'm down for that. So if we kind of, I guess you're saying I should dump this and instead think about it as 1 over the square root of mu.
I think I know what I did.
Okay. Did you flip the pieces individually?
I think I forgot to add the plus c until later, because what I ended up happening is I ended up getting ye, because I substituted back in from you. I got ye to the negative x squared over 2 equals e to the negative x squared over 2 divided by e to the negative x squared over 2, and got y equals 1.
Yep. So now if I flip both sides over, I have the square root of mu is 1 over a constant minus e to the x squared over 4. And yeah, I think what Ethan, I think what you're saying is that if you introduce the constant later, it ends up in the wrong spot. Is that basically true?
Yeah, basically you end up getting just y equals c. Or
Yeah.
sorry, y equals 1 plus c, because you're able to divide by something that you shouldn't be able to.
Yep. And then here we just square everything. So we get mu is 1 over c minus e to the x squared over 4 all squared. Okay, then what?
Back substitution for mu.
Yep, so I'm going to need to pick that thing up. And let's see. So then I went back up here and I'm looking at what y was. So at the end of variation of parameters, so variation of parameters ends with y equals mu times e to the x squared over 2. And yeah, you're right. If the c is not in the right spot, then this will look a lot like it cancels, and then you'll assume that y is a constant, I guess, which is super easy to do. All right, so am I done with this problem with this variation of parameters ends with this?
Not quite. You have to do the solution for the constant.
Yeah, way up top they told me y of 1 was 4. So I need to be plugging y of 1 equals 4. So that would be 4 is 1 over, and I guess I've got my c minus, let's see, so what do you get when you plug that in there?
E to the 1/4.
E to the 1/4 squared. And then on the top, I have an e to the 1/2. And this is kind of nasty, right? But I mean, you go solve it for a number, right? So if we do a little algebra here, the first thing we're going to do is we're going to divide e to the 1/2 over. So we're going to have 4 e to the minus 1/2 is 1 over c minus e to the 1/4 squared. Then we need to square root both sides. So we're going to get 2 times e to the minus 1/4 is, I guess I chose to square root both sides a little early, whatever. So you get this. Then you need to flip both sides over. So I'm going to get e to the 1/4 over 2 is c minus e to the 1/4. And then this needs to go to that side. So I think all told here I end up with c is what, 3/2 e to the 1/4? Roughly speaking, this crap is arithmetic. Well, okay, it's not arithmetic, it's algebra, I guess. Should maybe
It involves variables, so.
Be a little bit less cavalier about this, but yeah, this whole step here is some like real hard algebra. Maybe not real hard, just real easy to mess up. Are those the same thing?
I don't think so.
Yeah, I think it's maybe just error prone.
If that's the case, then anything involving a negative sign is very difficult.
True.
Yeah, anything with an exponent in it that's not like 2. And even that.
I hate fractional exponents so much.
Okay, so from here we went and did a back sub. All right. Any questions on? Well, I guess I didn't finish this. What's my last step?
Resubstitute C.
Yeah, so we'd have to resub this thing. And so in the end, we get y is, and then I'm gonna be a little bit lazy here. Okay. So we stick our number in there. We circle this puppy. Then on to the next problem. Any questions on this deal?
Nope. I wanted to know where I went wrong, and that's where I went wrong.
Yeah, so the important thing is, I guess if I had to recap for other people, this C needs to appear here. So the word of caution is something like, be sure to add your constants when you anti-differentiate. Not later. In other words, you can't just assume it's going to be a plus C later, because it'll probably be a plus C somewhere, and then arithmetic or algebra will happen to it. And it is a little easy to get screwed up because they are kind of arbitrary constants, and there are some special rules for those. So it's easy to get that like, oh, is this a special rule for arbitrary constants thing? Like here, if I flip it over, it's pretty common for students to just put the plus C on the top here. And that just is not quite the way they work.
I think that may have been what I did.
It's a really easy mistake to make. That's one that I'll even occasionally screw up if I'm moving fast and not thinking very hard.
I just try to remember that it's conjoined by PEMDAS, which is like the first algebra trick you learn. Because
Nope.
it's no.
No, I refuse to believe in PEMDAS. Where are the parentheses in this?
Whatever, Gemma, whatever.
Just get rid of like half the operations in PEMDAS, and then you'll get a good acronym.
Yeah, I'm really offended by the P part of that, because it's like fundamentally it starts with parentheses, except like for all the times when it doesn't start with parentheses, which is like most of the times.
I still do put parentheses around a lot of my terms.
Yeah, and you
If
should.
yeah.
The
Yeah,
only
it's
the only
just
time I
that-
ever like end up using parentheses is with binomial coefficients and trigonometric functions.
Yeah.
Yeah.
I was gonna say it's just because we're mathematicians and we're lazy and don't want to write parentheses for every single term.
Because we'd end up with like 5 layers of parentheses.
Yeah, yeah. If I wrote parentheses around everything in here, it'd look like a piece of Lisp code.
Ouch. At least it's not Perl.
Yeah, fair. What's the? Isn't there a Isn't there isn't there one of the brain hack languages that's just parentheses and brackets?
Yeah, it's brainfuck.
Oh, perfect. All right. Any other questions in the 2.4, 2.5, 2.6 kind of realm?
I have one for 2.6. I was gonna ask 3, but I think I'll try to get the other 2 on my own.
You were going to ask 3 out of where?
2.6, but I just have one.
Okay.
If anyone has anything before that, though.
I had another one from 2.4, but I'm willing to wait.
Oh yeah, sure. Hit me while I got it up here.
2.4, number 55.
Whoa, that's going to be scary. I'm not sure that's a good idea. Who assigns problems that far down? Aren't they hard?
I just realized I didn't do 55. I turned it in without doing it because I didn't size it.
So did I. It's
Oh,
just because I
wait.
got frustrated with it.